Before we get to our standard zoo of predictive analytics models, let's review exactly what we're computing about each model in terms of how well it's performing. What metrics are we actually looking at in terms of errors? So if our model is predicting a numerical response, like income, GPA, amount purchased, etc., then we're going to be comparing models RMSEs, which is short for root mean squared error. And the way that I like thinking about the RMSE is that it's just the typical size of an error made by the model. So if we're trying to predict, say, the lifetime value of a customer, and we find that a model that we like has an RMSE of $411, that means that the predictions are typically about $411 off from the true lifetime values of the customers. And so whenever our result is a numerical response, that's what we'll be comparing between different models, and we'll focus in on that. It's a little bit easier to actually compare numerical response models because there's only really one thing that we look about, that root mean squared error. If we're doing a classification model instead, say if we're predicting if someone donates versus not donates in a particular year, if they click on an ad, they don't click on an ad, they churn, they don't churn, etc., well, there's a bunch of different things that we can measure about classification models that we might be interested in selecting a model based on. Number one might be the model's misclassification rate. So if the model makes 1,000 predictions, what fraction of them are incorrect? That's the misclassification rate. And the accuracy is going to be the fraction of those 1,000 predictions that it gets correct. And typically models with higher accuracies are in some sense more appealing than models with lower accuracies, but there can be a bit more to the story. There's a few other metrics that we sometimes are interested in focusing in on. One of those is focusing in on the false positive or false negative rate. So for example, if we were designing some sort of predictive model that essentially opened up an email, scoured through the words, the character frequencies, the punctuation frequencies, and made a prediction as to whether or not that email was junk or safe, well, it's not the overall accuracy of that model that's going to be the most important to us. One thing that's going to be very important to us is that all the safe emails actually make it to our inbox. So one thing, if we're, say, counting a junk piece of email as a positive here, we want to make sure that the false positive rate is very tiny. We don't want a safe email coming off as a junk email, according to our model, getting siphoned away so we never actually get to see it. And so it's not necessarily the overall accuracy of the model that matters. It's more making sure that the safe emails actually get to us. We might be okay with a junk mail, a rogue junk mail or two getting in there. Sometimes we want to minimize false positive rates or false negative rates depending on the context. And in fact, very often when one type of error is actually a bit more important for us to detect than another, very often we end up looking at the model's AUC, which stands for area under the curve, and I'll get into that in a second here. But it essentially is letting us know how well the model is ranking the probabilities. So if we have members of the yes class, we have members of the no class, on average we would like the assigned probabilities belonging to the yes class to be higher for those individuals actually in the yes class than in the no class. We want to have those junk emails having a higher score for being junk than safe emails here. And the AUC is really good for kind of fleshing that aspect of the problem out, making sure that a class that we're particularly interested in detecting ends up with higher scores or higher probabilities according to that model here. And very often in business analytics, this is where we want to be. Thinking back to the KK-Box churn example, the churn management team is probably interested in each day sitting down and looking at the 1,000 customers most likely to churn. In that case, we're really more interested in the customers that will be churning, actually receiving high probabilities of churning according to the model, at least higher than the ones that aren't churning. And so whenever we're asking for something like, well, give me the top 500, give me the top 1,000, the AUC is actually something that we'll focus in on. But as you can see, when you're doing a classification model, yes versus no, there's a few things to think about. It's not quite obvious what you should be comparing between models and really using as your final evaluation. That's really going to depend on what you want out of the model entirely. So let's talk about that misclassification rate and the false positive, false negative rate. Usually when we evaluate a classification matrix or a classification model, we look at the confusion matrix. And the reason why is that there's actually two ways that a model can end up getting it wrong. So we might have in actuality that someone belongs to the no class, but the model actually ends up predicting yes. That would give us an incorrect response. And likewise, if the model predicted that someone belonged to the no class, but in actuality they belong to the yes class, that's also a second way of getting it incorrect. So if in actuality we're dealing with a safe email, but the model predicts that it's junk, that's one way to get it wrong. If the model is predicting that it's a safe email, but in actuality it's junk, that's the other way of getting it wrong. There's a bunch of different ways to break down those two different errors. So the confusion matrix essentially tells us everything that we need to know about the accuracy, the misclassification rate, false positive, false negatives, etc. And if you look at that matrix, you can actually translate between the two of them. So one thing that you're going to want to make sure that you can do is to look at a confusion matrix and compute these quantities just on the fly. So here's an example that is taken from the PIMA diabetes data set where we're trying to predict whether or not a woman has diabetes or not based on some of her physical characteristics. So there's about 400 women in this data set. And in this case, there's 124 that have diabetes and 286 that don't. So when we compare the reference, essentially the actual class, versus the predicted class, here's what ends up happening. So when the woman doesn't have diabetes, well, the model correctly predicts that 238 times. When the person does have diabetes, the model predicts that 100 times. So what's the accuracy? Well, those 238 times plus those 100 times divided by the total number of predictions, or about 86%. The misclassification rate would just be 100% minus that. Looking at the off-diagonal elements here, looking at the 30 and 24 here, essentially predicting yes, but in actuality, no, woman doesn't have diabetes. And then when the woman has diabetes, but the model says no, we have 54 total errors out of 392 predictions. So that misclassification rate is going to be right at about 14%. Now, especially in the medical industry and in business analytics, usually we're more interested in making sure that our model is really good at detecting one particular class. So if we're interested in doing some sort of screening for diabetes, well, one of these two errors kind of matters a bit more than others. And I would say that this box right here is the one that's most problematic. If a woman has diabetes, we want that model to come back and say, yeah, she does. So these false negatives here, where the woman has diabetes, but the model's predicting no, a negative response, is in some way the error that we want to avoid. Maybe we want to tune our model to help minimize that false negative rate. What is that false negative rate? Well, we can calculate it just by looking at the number of false negatives, 24, the number of times the model predicted no, but in actuality the woman did have diabetes, and divide that by the total number of women that were actually in the positive class here. So a false negative means the model predicted no, but in actuality the person's yes, so our denominator would be all of the women that do have diabetes. And so 24 out of 124 is about a false negative rate of 20% here. About 1/5 of the women with diabetes get missed by that model. All right, so misclassification rates, accuracies, false positive, false negatives, that's one way of looking at that problem. One thing to always keep in mind, though, is that just because a model has a high accuracy, like what we have here, 86% sounds pretty good, we always have to ask, well, what's the baseline rate in the data set? In other words, what would the naive model that just predicted everyone to belong to the majority class achieve in terms of its accuracy? So in this case, we know that the no class is the majority in the data set because 268 women don't have it versus 124 that do. So if the model just straight up predicted no for everybody, well, what fraction of predictions would it get correct? Well, it would get 268 of those predictions correct, divided by the total number of predictions it made, or about an accuracy of 69%. So if any model can't beat an accuracy of 69%, you're kind of wasting your time. And so this model right here is worthwhile in some regard because if we're gauging the model based on terms of accuracy, its accuracy is substantially higher than that of the naive model. And so that's one thing to always keep in mind is that if you do choose to compare models' accuracies, make sure that the accuracy is better than the naive model. Just looking at the accuracy by itself isn't informative directly. So one more example just to hit that point home, let's imagine that we had a very imbalanced data set where there's a big difference in the number of yeses versus nos. So let's imagine that 98% of the individuals are members of the no class, only 2% are members of the yes class. Well, if you fit a model and you get an accuracy of 97%, well, on the surface that sounds like cause for a celebration. 98% is pretty darn good, but actually that's better than that's worse than the naive model. The naive model that just says, nope, everyone's a member of the no class would achieve 98% accuracy. So just be careful with accuracy. Always be interpreting that with regards to what the naive model would be doing. What fraction of the individuals in the data are members of that majority class. If you can't beat that accuracy, then you're wasting your time. All right, the other way of evaluating models, and this is one we very often turn to in business analytics, developing a churn management system. If the alumni office wants to know, hey, give me a list of the 100 most likely alumni for donating $1,000 or more this coming year, the AUC is what we'll be tuning our models on. Whenever we're more interested in kind of fleshing out a set of individuals with the highest probabilities, the AUC is kind of where it's at. So what is this AUC? Well, technically it's the area under the ROC curve. We can gloss over what the ROC curve is because here's a kind of a nice definition that I like keeping in mind. Now it's rather verbose, like a lot of things in business analytics and statistics, but here we go. Here's how we can interpret what the AUC means. So the way that we interpret it is that we imagine picking an individual at random from the data that belongs to the yes class, and then we also pick an individual at random from the data that belongs to the no class. So the AUC is tied in to the predictions that the model makes for each of these two individuals, one from the yes class and one from the no class. So if we think about it, we would like the model to come back with the predicted probability that's higher of belonging to the yes class when we're dealing with the yes individual than if we were dealing with the no individual. And so the AUC tells us this probability. This AUC tells us the probability that the model actually gives the individual from the yes class a higher probability than the individual from the no class. So if you're working for KK Box and you're trying to figure out who are the most likely churners out there, well, your positive class would be the churners, that's your yes class. You want to make sure that your model is assigning higher churn probabilities to those that actually belong into the yes class, the churn class, than in the no class. You don't want to be kind of throwing money away by offering special offers to the people in the no class if they ended up getting higher probabilities of churning than the actual churners in the data. So kind of a long-winded interpretation, but very often exactly where we want to be in business analytics. We want a list of the 500 customers most likely to churn, most likely to donate, etc. And that AUC is what we'll be focusing in on. So wrapping this up, how do we choose between, say, accuracy and choosing between AUC? Well, we just need to think about what we want out of the model. So if we think that both types of errors, false positive, false negatives, are equally as bad, then AUC, or accuracy, is fine to use. If one type of error is a lot worse than the other, then typically the AUC is generally preferred. So the diabetes example, the junk mail example, donation example, churn example. A lot of examples in business analytics here. What's an example of, say, when accuracy would be fine? Maybe click-through rates. We're not really interested in, say, one particular class versus the other. We want to have more clicks, but from a kind of false positive, false negative rate point of view, they're about equally as damning for the model when they end up missing those. So, if I were to predict a click-through or yes versus no for click-through, I would say accuracy might be fine with tuning models on. And then finally, if you're more interested in the ranks of these probabilities, not really the probabilities themselves, as long as, say, the churners in the data set are getting like a 5% chance of churning, And the non-churners are getting like a 1% chance of churning. Well, 5 is higher than 1. They're kind of ranked correctly. Then that's really what we're after. From a procedural point of view in Caret, this is as easy, switching back and forth between AUC and accuracy is as easy as just changing one line of code. So we just need to make sure that we know what we're doing. And it just is tied into the context of how we're evaluating these models. So there we go. I think we're ready now to dive into our zoo of predictive analytics models and talk about how Caret can really streamline the procedure of just auditioning all of the models, all the different flavors of those models, and then coming up with what our final choice should be.